So in this video, we're going to talk about Euler's formula. And one of the things I want to start out with is why do we want to talk about this rather odd looking formula? What's the big deal about this? And there is a big deal, and the big deal is E. We love E. And I'll underline that twice. Now the reason is because when we take a derivative of E, dt of e to the x equals e to the x. And ddt of e to the ax, so where a is anything, equals a e to the ax. And so the property is that when you take a derivative of the function, the same function comes out. Or if you take a derivative of the function, a scaled version of the same function comes out. And we love this because why? Because when we do differential equations, e to the x is the solution. Almost every time. Whenever we did a circuit, e to the x was the answer. If you recall from when we were solving circuits, simple circuits with differential equations, that we always said something like, well, we're going to guess that v of t is some constant times e to the st. That was a proposed solution. This turned out to work every time. So there's something else we love too, and that is sinusoids, or sines and cosines. Okay, we love these. And that gets 2 lines. Now, why do we love these? It's because they happen in nature. If you whistle, the air pressure looks like a sine wave. If you ring a bell, the bell moves in a sine wave. Any kind of music. If you look at the notes in music, the sound they make, the pressure waves look like sine waves. And circuits make sine waves. Remember, we analyzed this circuit in great detail. It was the LC circuit. We looked at the natural response of this, and that was a sine wave. Okay? So electric circuits make sine waves. All these things make sine waves. They occur in nature, and we want to be able to analyze things that happen when sine waves are present. So we have 2 things we love, and we want to relate these 2 things. And these are going to be related through that, Euler's formula. That's how we connect these 2 separate ideas. And let's go do that. So Euler's formula says that e to the jx equals cosine x plus j times sine x. So Sal has a really nice video where he actually proves that this is true. And he does it by taking the Maclaurin series expansions of e and cosine and sine and showing that this expression is true by comparing those series expansions. Now, I'm not going to repeat that here. We're just going to state that as fact. And now we're going to look at this equation a little bit more. So this is the expression that relates exponentials that we love to sines and cosines that we love. And part of the price of doing that is we introduce complex numbers into our world. Here's 2 complex numbers. Okay, this is where complex numbers come into electrical engineering. So I have to mention the other form of this formula, which is e to the, I put a minus sign in here, e to the minus jx, and that equals cosine x minus j sine x. So these two expressions together are Euler's formula or Euler's formulas. And we're going to exploit this by we'll be able to take the cosines and sines that we find in nature. We're going to be able to fashion them into exponentials. And these exponentials then go into our differential equations and give us solutions. And we're going to come back and pull out the cosines and sines. That's the rhythm of how we're going to use this equation to help us solve circuits. One small point I want to share. Notice that in both these equations, the cosine comes first and the sine is over here. on the imaginary side. So the cosine is on the real side. This is the reason that we have a preference in the future. We're going to have a preference for talking about our real world signals in terms of the cosine function. It's because in this Euler's formula, the cosine comes first in both cases. So what I want to do now is take a second, and I want to see if we had our signal expressed in these exponentials, how do we recover the cosine and the sine term? How do we flip these equations around so we can solve for the cosine and the sine? It's a simple bit of algebra here. It's good to see. All right, so if I want to isolate the cosine term, let me get rid of these guys here. So now to isolate the cosine term, what I'm going to do is add these two equations together, and that plus and minus are going to cancel out this second term here. That's what I'm going for. So if I add, I'll get e to the jx plus e to the minus jx equals cosine doubles